Okay, so we're going to continue with our work in thermodynamics, and today we're going to discuss Gibbs free energy and spontaneous reactions. So we discussed that spontaneous reactions as a function of entropy, right? So we're going to take that a step further, and we're going to talk about the Gibbs free energy, and basically what that gives us is the net effect of the spontaneity of the enthalpy and the entropy changes in a given reaction, right? Now, to kind of focus on this a little bit, we're going to talk about the second law of thermodynamics. And the second law basically states that whenever a spontaneous event occurs, right, it is immediately followed by an increase in entropy, right? So spontaneity and entropy go hand in hand. Now, Gibbs energy is defined as the energy in a change that is free or available to do work. It's defined as a function of enthalpy H and entropy S with temperature. So let's take a look at what Gibbs free energy kind of looks like, right? So if I have Gibbs free energy, which is represented by the variable G, that's going to equal H minus TS, okay? Remember that G is going to be equal to Gibbs free energy okay? H is going to be equal to the enthalpy. S is your entropy. And T, of course, is going to be your temperature in Kelvin. Okay? Now, G and H, right, and S are not absolute functions, meaning that they are functions, but they're not absolute. So we kind of have to rewrite this in a way, right, because we have to find it. So it makes more sense to write it as the change in the Gibbs free energy is equal to the change in the enthalpy minus temperature times the change in entropy, right? Now, remember that delta means change, so delta G quite literally means your G final minus your G initial. And this is exactly what we talked about when we talked about entropy, right? Okay, so here's how this stuff breaks down, right? A change can only be spontaneous if it's accompanied by a decrease in the free energy, meaning that as a reaction moves forward, right, if it's moving forward spontaneously, meaning without outside influence, whatever free energy is available to do any work is going to get used up, right? So in order for a reaction or an event to be considered spontaneous, then we're going to write spontaneous. Then the delta G must be negative, right? It must be negative. Now, if delta G is equal to G final minus G initial, what that means is that the G initial must be greater than the G final in order for this to be a negative delta G and give us a spontaneous reaction, right? Now, let's take a look at what does this mean in terms of enthalpy and entropy, right? So let's take a look. Change colors here. If I have delta H, right, here's what this is telling us. If delta H is negative, right, going under this equation. If delta H is negative, and if delta S is positive, then delta G equals delta H minus T delta S, right? It's going to look like this. Negative minus temperature times a positive, right? Now, if you have a negative minus a positive, then what that's going to do is you're going to end up at delta G that's going to be negative. If that happens, then this reaction supports spontaneity. We're going to say that this is spontaneous, right? It's a spontaneous reaction. Now, remember that entropy is the increase in disorder, and enthalpy is the either energy absorbed or released, right? So think about it like that, all right? If delta H is releasing energy, right, because that's where it's negative, that means that it is exothermic. So energy is leaving the system. Now, if energy is leaving the system, then you're increasing the disorder of that system. So like the ice cube melting, as the energy is going out into the system, right, then the disorder of the water molecules is increasing. And as a result, right, you're going to have a spontaneous reaction, which is going to result in a negative delta G, right? Let's look at the other side. Let's say I have delta H is positive, meaning that it is absorbing energy from the system, right? Delta S in this case is negative, right? Because if it is absorbing energy from the system, it is decreasing the disorder, right? So that's going to be negative. And if I have delta G is equal to delta H minus temperature, right, times entropy, then it kind of looks like this. A positive value minus a negative value, right, is going to end up positive if this number is bigger, right? So this is going to result in a positive delta G. Now, how is this positive, right? Well, think about it. If you have temperature times a negative, this makes this whole value negative. And if you have two negatives, then those two negatives really become a positive, so you're increasing a bigger number, right? So you're increasing the number and it's making it bigger. So regardless of the temperature here, because remember, Kelvin temperatures are all positive. If you have a positive H, delta H, and a positive or a negative delta S, right? Because you're subtracting them, you're going to end up with a positive delta G. Now, if that's the situation, then this reaction is going to be non-spontaneous. Right? It's going to be a non-spontaneous reaction. All right. Now, let's take a look at one more scenario. Right? Let's take a look and see if we have, let me get rid of this here real quick. Okay. Sorry about that. Okay. So let's say that both of these are the same, or both of these are positive, right? So let's go back and let's do delta G is equal to positive delta H, right? And a positive entropy. Okay. So when this situation happens, right, this is where temperature begins to play a role, right? So when delta H and delta S have the same sign, the temperature becomes critical in determining whether or not an event is spontaneous. So in this situation, both delta S and delta H are positive. So only at a really high temperature will the value of T delta S be larger than the value of H. So then that difference makes G negative. So in this situation, right, when this is bigger, right, when T delta S is greater, right, than delta H, then delta G is negative, right? So this has to happen at high temperature. Does that make sense? Let's take a look what happens if both are negative, right? So again, remember that you're subtracting, and this negative is going to make the whole value of, let me see here, T delta S negative, right? So basically, you're going to be adding this one. Now, in this situation, right, then the temperature again plays an important role. Because if the temperature is high enough, right, to bring this number where delta S, T delta S, is greater than the enthalpy, right, then again, you're going to have a spontaneous reaction. Right? And just the reverse is true. If the T is not big enough, right? If the T is not big enough and it ends up that delta H is actually bigger than the T delta S, then your reaction becomes, your delta G becomes positive, which makes it non-spontaneous. Right? So we have to pay attention to that kind of stuff, right? Now, most of the time, you're going to actually calculate this out, so you'll know whether or not you got a delta G, positive or negative. But here's what we're taking away, right? Delta G positive equals non-spontaneous reaction. And if delta G is negative, then you're going to have a spontaneous reaction. Right? That's the takeaway. All right. So let's take a look. Let's do a little table here and see if we can figure this out. Let's see. We're going to insert a table. All right. And we're going to make it where we have, let's see. Okay. All right. So let's say we have a positive and a negative delta H, right? Then we have a positive and we have a negative delta S, right? So if both are positive, it's going to be spontaneous at high T. Let me do this in a different color. At high temperature. If entropy is positive and enthalpy is negative, then it's going to be spontaneous all the time, regardless of temperature. If delta H is positive and delta S is negative, then it'll be non-spontaneous, right, at all temperatures, regardless. And if they're both negative, it'll be spontaneous at low temperature. Mm-hmm. It'll be spontaneous at low temperature, which is what we were saying here. Okay. So let's put this into practice, right? Let's put this into practice. We had the reaction that we did before. It's here. We did this one in class. CO NH2. In solution, this is the urea, reacts with pure water to produce CO2 gas plus ammonia. Okay, so this is the reaction we did earlier. So what we're going to do is we're going to find delta G. We're going to find delta G. All right. Now, the formula for delta G is equal to the change in enthalpy minus the temperature times the change in entropy. Now, just like before, right, what we're going to do is we're going to rewrite this to find the standard free energy using standard heats of formation, right, and standard entropy. So what that looks like is delta G at standard temperature and pressure, right, is equal to standard enthalpy minus temperature times the change in standard entropy. So that's going to be the formula that we use, okay? All right, now we're looking for delta G, which is this one right here, okay? We need to find delta H in order to do this, and we're going to use the tables to find these values, right? So let's take a look at a table. Okay, so I have the tables right here. Okay. Now remember to find delta H, right? Delta H, standard heat of formation, is equal to the sum of delta H of the products minus the sum of delta H of the reactants. All right? We can rewrite it as delta H is equal to the sum of the products minus the sum heat of formation of the reactants. Okay? So let's find our values, right? So I wrote next to the wrong table, but let's come up here. Okay, so here are my delta H, my heats of formation. Now, in this one, here, let's highlight the ones that we're going to use. Now, we're working with CO2 gas as one of our products. So that's going to be this one right here. Right? Okay. We're working with ammonia gas, which is this one right here. Okay. We also working with pure water, liquid water. So we're going to find that. And that one is going to be, here we go, liquid water. Okay. And then finally, we're going to look for urea. So urea is right here. And it's going to be in solution. So we're going to use, let me see here, this one. Okay, so those are the four values from the table that we're going to use, right? So let's go ahead and find delta H. Okay, so delta H is going to look pretty much like this. Delta H is going to be equal to the change in the heat of formation of CO2 plus 2 times the heat of formation of NH3 minus the heat of formation of urea plus the heat of formation of water. This is going to be liquid. Okay? So this is our equation. All right? This is our equation. Okay. So now what we got to do is we got to plug in these numbers. All right? So let's plug them in. Delta H is going to be equal to 1 mole times negative 393.5 kilojoules per mole plus 2 moles times negative 46.19 kilojoules per mole minus 1 mole times 319.2 kilojoules per mole plus 1 mole times negative 285.9 kilojoules per mole. Okay, remember that moles are going to cancel. Here, 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 and here. Okay, So let's zoom out a little bit so we can see our equation. And there we are. Okay, so pause the video, right? Make sure you got everything written down correctly. And we're going to go ahead and simplify everything. So if I simplify this here, I'm going to end up with negative 485.9 kilojoules minus 605, negative 605.1 kilojoules. And if I simplify that even further, I'm going to end up with plus or positive 119.2 kilojoules, okay, is equal to my delta H. Okay, pause the video if you need it. Okay, so now we plug it into the formula. We know that delta G is equal to the change in enthalpy, right, minus temperature times the change in entropy. Now, we calculated the change of entropy of this reaction in class, right? So we already have that value. So to find the delta G, we simply take the new value that we have here, which is plus 119.2 kilojoules minus the temperature. Remember, standard temperature is 298.2 K. Okay, times the delta S that we calculated before, which in this case should be 0.3548 kilojoules Kelvin. Okay, these are going to cancel, right? If you have the kilojoules in the same unit, you should be able to subtract them. So if we take those together and we subtract them, we're going to end up with positive 13.4 kilojoules, right? This reaction is non-spontaneous. Okay? And that's it. That's how it works. Okay, if you need to use a value of delta H, you're either going to be provided a table or you're going to be provided the actual number. Overall, it's a matter of just plugging in the numbers and simplifying down to the final number. Just like enthalpy, okay, delta G can also be calculated using the standard free energies of formation for typical substances, right? So what that means is that delta G, let me see here, yeah. Delta G, standard delta G is equal to the sum of delta G of formation of the products minus the sum of the standard free energies of formation of reactants. Right? It's the same formula. It's the same formula. So when you guys come back into class, we're going to go ahead and calculate the free delta G using the standard free energies of formation. Okay? Here's the problem. We have a reaction that is C2H5OH, right, which is ethyl alcohol. This is going to be pure liquid, plus 3 moles of O2. And that's going to produce 2 moles of CO2 plus 3H2O. Okay, this is the reaction that we're going to work on. Okay, here's the chart with your standard free energies of formation. Pause it, find the ones that we need, and work on this, and then we'll double check it tomorrow in class.